Okay, so energy stored in a capacitor. How to find out the energy stored in a capacitor? Let's take example of a parallel plate capacitor, but this will be valid for any type of capacitor. Let us say there is a capacitor between 2 points A and B, and now these 2 points A and B are connected with a battery or a cell. Okay, its voltage is V. Now what happens is that as soon as you connect it, it will take some time to charge, and let us say that charge is building, and initially charge was 0. After some time here positive charge plus small q minus small q, charge is building up. Finally charge will become maximum. After that it will not get charge. So this is called charging of a capacitor. As soon as you connect with a battery, it will take some time for getting charge, and once it becomes fully charged, after that charge will, it will not store any extra charge. So there will be a maximum charge. That charge, you know, q equal to c into v, but it will take some time. So idea is that battery has to send charge, right? Suppose battery is sending charge. Let us say charge right now is q. Battery is sending small charge dq. So dq charge is getting deposited over the positive plate, and minus dq will deposit on this plate. So finally it will develop plus q minus q charges. So battery is doing some work. What is the work done by battery? Work done by battery. Work done by battery is supplying a charge of dq across a potential difference of v. So work done is charge dq into the potential difference v. Charge into potential difference, that is the work done, right? Now this work done, let us say this is work done is the stored energy du is nothing but the work done by battery is stored as a potential energy. Right? So we can integrate this. So total energy which will be stored is here dq, and v can be written as, because c is the ratio of q by v, so from here v can be written as q by c, right? So u will be equal to half 1 by c. Q dq integration is q square by 2, and initially charge was 0, finally charge is capital Q. Okay, so the energy stored formula will be half q square by c. This is the energy stored, and this is the work done by battery. Okay, work done by battery. So this formula can be written as, and of course here it is capital Q, not small q. This is capital Q. Okay, capital Q. What is capital Q? Is the total charge stored. Capital Q is C into V. We know that already. So you can now substitute in terms of Q. Q can be written as half CV. So energy can also be written as half CV square. Or I can write this as half Q by C I can write as V. So half Q into V also I can write. All these are different ways of writing that. Half C V square, half Q into V, half Q square by C. Clear? This is the way how can we write energy in different manner. Are you clear about this? Okay, now how to find out the heat energy lost, heat energy dissipated in charging a capacitor. Heat energy dissipated. So the heat energy dissipated is calculated as heat energy dissipated is equal to work done by battery, work done by battery, work done by battery, work done by battery, that is of course loss of heat. Battery is giving this work. Hmm. Previously, how much energy was there in the capacitor? Capacitor has no energy. Capacitor has got this much energy, right? C into V. And energy which is stored is also half Q into V. So battery work done by battery, work done by battery. Hmm. See, I think one minute here, what we have written now, this is work done by battery is no, this work done, it is like it's the energy stored, not work done. I think correct this one. This is energy stored, energy stored formula it is. Energy stored in capacitor. Energy stored in capacitor. Du. Okay. Work done by battery, how do you calculate? See, battery is sending a total amount of charge capital Q and voltage is V. So work done by battery, that separately charge into voltage. Okay, note that work done by battery, work done by battery is equal to charge into voltage. Okay, because battery potential difference is V and total charge battery supplying is capital Q. So capital Q into V is the work done by battery. And this integration that we are doing is the energy stored in the capacitor, because in the capacitor, what is the energy stored? So potential difference is V only, but charge is coming slowly. It's not that suddenly that charge Q is coming. So charge is coming slowly. So work done inside the capacitor is dq into V. This dq you have to integrate because charge is changing. Voltage is constant but charge is changing. So that's why this is the energy stored. So energy stored half Q into V or this, and that is the work done. They are different things. This is what we need to know. And here see how to calculate work done by battery. Suppose this is a battery plus positive terminal, negative terminal. Suppose this battery is supplying a plus Q charge from positive terminal, plus Q charge is coming out. So work done is Q into V. Suppose the battery is, sometimes what happen now, this uh, positive charge enters into the battery. Positive charge enters into the battery. In that case, work done by battery will be minus Q into V, because when positive terminal supplies positive charge, the work done is positive. But when the positive charge is going inside the positive terminal, that is the negative work done. So we should remember this fact. Okay. So this calculation, work done by battery, is a separate calculation. Okay, and energy stored in the capacitor, that is separate calculation. Okay. Now coming to the heat dissipated. So heat dissipated formula is given by this work done by battery minus this, remember that, from minus change of energy, minus change of energy in the capacitor. Okay, very important formula it is. Many people get confused with this. So energy dissipated, heat energy dissipated when you switch on the circuit is the work done by battery minus. Now you calculate work done by battery. Work done by battery we have calculated Q into V. Very simple, Q into V. And change of energy means what is change of final minus initial. So final energy in the capacitor minus initial energy in the capacitor. Initially capacitor has no charge, so initial energy was 0. We should know that initial energy was 0 because capacitor was not having any charge initially. But suppose in some cases already capacitor has charge and then you are connecting with a battery, then you have to take some initial energy in the capacitor. Okay. Anyway, and final energy, this is the formula which we have to use it. So Q into V, and energy stored I can also write as half QV. So this becomes half QV. So basically the energy total heat dissipated will come as QV minus half QV will become half QV. Okay, this is the heat energy lost or heat lost. Heat lost. Now you can substitute Q as C into V and all that. So you may write this again as half C V square or Q square by 2C. You can write these things. But the derivation, this approach we should note here. The work done by battery will calculate minus the change in energy in the capacitor. That's how this total heat calculation will come. Are you clear about this? Okay. Now using this idea, let us do some more calculations of different types. Some standard cases we can derive. Let us say that there is a capacitor. Let us take capacitor, and this capacitor was charged using a battery. Voltage is V, let us say. So it will develop plus Q minus Q. Its capacitance is C, or its capacitance is C1, let us say. So it will develop a charge. It will develop a charge, let us say Q1 plus Q1 minus Q. So this charge Q1 is equal to C1 into V, or if you want battery, you can write V1. Okay, so it will have this charge. Now after that, let us disconnect the battery. Battery is disconnected. So it will have this charge. This capacitor C1 have this plus Q1 minus Q1 charge. Now this battery is disconnected now. After disconnecting this battery, you are now connecting with another capacitor. Now identical or a different capacitor, let us take. Its capacitance is C2. Okay, and if you want, you can also consider its charge also plus Q2 minus Q2. It was also charged with a battery similar to this. So this charge Q2 is equal to C2 V2. Okay, just like the first capacitor was charged with a battery and it got charged C1 V1. Similarly, second capacitor was also charged with a separate battery. It got charged Q2, which is C2 V2. Now what is going to happen? These two terminals are going to be connected. Now let us connect these two terminals. Okay. So once you connect these two terminals, these charges will flow between them. Charges flow will take place, and after that finally some charge will be there. Finally what will happen? I will draw the final circuit. So finally on this capacitance C1 and on this capacitance C2, some charges will be there. How much charges we do not know. Let us say this is Q1 dash plus Q1 dash minus Q1 dash, and here plus Q2 dash minus Q2 dash. Okay, minus Q2 dash. So some charges are here and here. I am going to derive a general formula. Okay. So initially first capacitor has fully charged using a voltage battery V1. So it has charged C1 plus C1 minus C1, C1 V1 plus C1 V1 minus C1 V1. Similarly, second capacitor was charged with another battery, right? Same way, it has got plus C2 V2 minus C2 V2. Now the ends are connected or short circuited. So finally some charges will be there. So let us try to find out the loss of energy. So we have to find what? Find heat loss, and and common potential. Heat loss and common potential. This is a very important thing. Heat loss and common potential calculation they will ask. So how do you calculate that? Common potential means it will develop now a common potential. Let us call that common potential as V. So same potential will be there. So first of all, note that the charges which here the total charges which are present, charges cannot be destroyed. So Q1 plus Q2 is same as Q1 dash plus Q2 dash. Total charge will remain constant. So the sum of this Q1 dash plus Q2 dash is same as Q1 and Q2, which is nothing but C1 V1 plus C2 V2. Okay. So now we know this sum of the charges. Okay, what are the charges present? We know sum of the charges we know. Now, how can we calculate the charge? We need one more equation, right? We need one more equation. How to calculate that? So we know that now they have got a common potential. So this Q1 dash is equal to Q1 dash is equal to C1 into V, and Q2 dash is equal to C2 into V. V is now the common potential which you have to calculate it. You can now substitute it here. This substitute that Q1 dash is C1V plus C2V is equal to C1 V1 plus C2 V2. So from here, and also note that this question in this case we are connecting positive terminal and negative. Sometime in the question they reverse it. You are connecting positive of first plate and negative of second plate. Then question will change. Okay, right? Here we are connecting same terminals, polarities. Okay. So from here V can be taken common and you will get the common potential formula C1 V1 C2 V2 by C1 plus C2. This is the formula for common potential. Common potential. Common potential. Okay. What about heat loss? How do you calculate that? What was the idea how to calculate heat loss formula? Heat loss formula is work done. So do we need to consider the batteries? Because see, once I have disconnected the battery, so here heat loss formula is what we are going to do is heat loss means we are not considering the initial, like during the charging of the capacitor. Charging of capacitor that we can use, but here heat loss, when are we calculating heat loss? Heat loss we are calculating when these two capacitors are connected, right? These two capacitors, you are assuming that initially already these two capacitors are charged, and then you are connecting these two capacitors together in parallel, right? Basically you are connecting them in parallel. So while connecting these two capacitors, what is the heat loss? That is the question. Okay. So heat loss while connecting these two capacitors. Heat loss while connecting the capacitors. Capacitors. Okay, so when you want to calculate heat loss, one capacitor and other capacitor are just connected, then your battery is not involved. Okay, battery is not involved here. So if you want to calculate this, battery is not involved, then you can simply consider that heat loss means initial energy of the capacitors minus final energy of the capacitors, right? That means heat loss here you can use simply as initial energy minus final energy. Initial energy minus final energy. Initial energy minus final energy. This heat loss is during the connecting the two capacitors. Okay, so let us try to derive a formula for that. So okay, what was the initial energy in each capacitors? And each capacitor was charged, right? So half, anything you can write. Let us write in terms of half CV square. So half C1 V1 square plus half C2 V2 square. These were the energy in the capacitor. First capacitor energy, second capacitor energy. Now final energy is how much? Final energy is how much? Minus final energy. So finally we can consider this as a system. Okay, note that you can also use half C1 V square plus half C2 V square. That also you can do if you want, but I will use a shortcut. What is that shortcut? The shortcut is I will try to calculate as half C equivalent into charge square. So total charge is the sum of charge. Note that Q1 plus Q2. I am going to write it like this: a half C equivalent into total charge square, right? Because this total charge only is distributed over each capacitor. They are in parallel, so C equivalent will be C1 plus C2. So let us now solve this. So half C1 V1 square plus half C2 V2 square minus half C equivalent is C1 plus C2 and Q1 plus Q2 total charge already we know. Total charge is C1 V1 plus C2 V2. So this is C1 V1 plus C2 V2 the whole square. Now you simplify this and get a formula for this. Try to simplify this. You have to open that square, okay? Then only you can do it. Half C1 V1 square plus half C2 V2 square minus. Let us open that. So a square b square plus 2ab it will come, right? C1. Anything can come common here. Suppose if I bring half C1 V1 square and then hmm, otherwise you have to open this. Nothing else we can do. Can we do some shortcut something here? Solve this question. Some shortcut can be done, I think. What is that? Otherwise you have to open it. Nothing can be done. C1 plus C2 you have to do and you have to open it. Huh? Or see, one shortcut can be if I can try to take and divide by C1 and C2 both, right? Some simplification can happen. Okay, you open this. Show C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2. Right? Open this. Open this and simplify. Half I will take common. Okay. Half I will take definitely common. It will become C1 V1 square plus C2 V2 square minus this is C1 plus C2. Now I can open this also. C1 I can open this. So C1 plus C2 can be opened here. So what do we get now? C1 I will multiply then. C1 cube, right? V1 square minus C1 C2 square V2 square minus 2 2 C1 square C2 V1 V2. Little bit lengthy it is going to be minus C1 square C2 V1 square minus um, C2 cube V2 square, right, minus 2 C1 C2 C1 square C1 C2 square V1 V2. Okay, this is what it is. Any simplification happens? Check. Do we get any simplified things? Anywhere, anything simplification happens or not? I think somewhere I made mistake. This unit wise it is not coming correct. Half equivalent V square we have to do. Oh, half equivalent V square I have to write now. Or Q square by 2 C equivalent. C equivalent should be divided here. Oh, okay, okay. C equivalent has to be divided here. That is why it is not coming. Should come. C equivalent should be divided here. Hmm. Q square by 2 C equivalent now. Q square by 2 C equivalent. C equivalent. Okay, do that now. So half C1 V1 square plus half C2 V2 square minus half. This is C1 V1 plus C2 V2 whole square divided by C1 plus C2. Now take calcium. Let us take calcium. 2 C1 plus C2 as calcium. Then C1 V1 square C1 plus C2 plus C2 V2 square C1 plus C2 minus C1 V1 plus C2 V2 whole square. Okay, then let us open this bracket. So C1 square V1 square C1 C2 V1 square C C1 C2 V2 square plus C2 square V2 square minus, open this, C1 square V1 square minus C2 square V2 square minus 2AB C1 C2 V1 V2 divided by 2 times C1 plus C2. Then what will happen? What terms is going to cancel out? C1 square V1 square C1 square V1 square cancel. C2 square V2 square C2 square V2 square cancel. Right? So what do you get finally? Okay, now I think C1 C2 term is coming common everywhere. Let us take C1 C2 common. So C1 C2 by 2 C1 plus C2 into V1 square plus V2 square minus 2 V1. Yeah, now it got a formula, correct? Hmm, yes. So heat loss in connection is equal to C1 C2 by 2 C1 plus C2 times V1 minus V2 whole square. Remember this formula? This formula now you have to remember. Remember, this formula is only true when positive terminals are connected and negative terminals are connected. Okay. Then you can work out problems on this. So heat loss topic is over. I think now capacitance is over. What else is remaining? Capacitance. RC circuit questions you can study after electricity. RC circuit right now you don't have to do that. Okay. So that's what it is. Now only thing is that you need to work out problems where heat calculations are involved. Okay. So let us try some questions on heat. Any question you have on the heat? Let's check that. I think dielectric insertion is also remaining. Dielectric. And yes, dielectric topic is also remaining. That also we have to do. Heat calculations. Capacitance, did I send you the worksheets on capacitance? Capacitance, did I send? Capacitance, yeah, capacitor worksheet I have sent it. Yes, check that. In that capacitor, any questions of heat is there? Definitely this worksheet is very good and lot of questions might be there here. There is a very good question number 35. Very good question it is. Let's solve worksheet question. First worksheet. A capacitor of capacitance is initially charged to a potential difference of V volt. Okay. So there is a capacitor. Now you have to solve this question. Okay. Capacitor is C and it is charged with a battery of voltage V. Okay. It is charged. Then now it is connected to a, so after charging you have disconnected this, after charging you have disconnected, so no charge will be seen to be, so plus CV minus CV charge will be there. Then what it is, now it is connected to a battery of 2V volt with opposite polarity. Now this time we are connecting with opposite polarity battery. This battery has 2V and now we are doing connection like this. Okay, this you have to understand. Now positive is connected to negative terminal, negative is connected to positive terminal. This is what we are doing in this. Okay, minus plus and this is plus minus, opposite terminals are connected. The ratio of heat generated to the final energy. So very good question it is. They are asking ratio of heat heat generated by final energy stored. Let us calculate this ratio. So first tell me, how will you calculate the heat generated? Heat generated, see here battery is also involved. Okay, so work done by battery minus change of energy. Change of energy. Change of energy. Okay, so first of all, you need to find what is the energy initially. Initially, this capacitor means we are considering the loss of gain here in this process, not in this process. So already capacitor was having energy. What was energy of capacitor initially? Initial energy was half CV square because it was charged with a battery. Half CV square. This was capacitor energy. Okay, finally note that once you have connected, finally this battery is connected. So final charge is C into battery voltage 2V. So finally, what will be the finally, if you think about it, finally will be what? Finally, this battery will finally send charge here. Okay, so final energy you can write as half C, but voltage has now 2V because a capacitor of C is connected with a battery 2V. So half C into 2V whole square. Half C into 2V whole square. This will be the final energy. Okay. So that means change of energy we can calculate. Change of energy means final minus initial. Final minus initial we can calculate. How much will be final minus initial? So half C, this is 4V square minus half CV square. Half CV square you can take common. Half CV square if I take common, then how much it is? Half CV square. 4 minus 1, 3 will come, right? So 3 by 2, that means 1.5 CV square. Okay. This is the change of energy in the capacitors. But the thing is that now you need to think about it. How much work is done by the battery? Now you have to calculate work done by battery. So because battery is involved here, this battery, not the first battery, second battery. So this battery, how much charge? See, previously I will here write. Okay, previously how much charge was there? Previously charge was plus CV minus CV. After you connect with this battery and after long time, the charge on this one will become plus 2 CV and this has become minus 2 CV. Okay, so how much this battery has sent charge? Now tell me how much this battery positive terminal is sent, because previously here was minus CV and now the charge is plus 2 CV. So how much this battery has sent the charge? Can you tell? No, no. See, this positive plate was having plus CV and negative plate was having minus CV. Now battery is connected in opposite manner. So this positive terminal is sending some charge, but finally the charge will be plus 2 CV and minus 2 CV. Why? Because battery voltage is 2V. So charge final is C into V. So but voltage is 2V. So C into 2V, that is plus 2 CV and minus 2 CV. So if you see this plate, let us see this negative plate which was initially minus CV. Now its charge is plus 2 CV. So how much charge battery has supplied here? Can you calculate? Plus 3 CV. Yes, correct. Because it was having minus 2 CV. If you add plus 3 CV, then only it will come plus 2 CV. Right. So battery has sent, positive terminal has sent positive charge plus 3 CV. Now work done by battery. Remember work done by battery, how to calculate? How much positive terminal is sending? It is sending plus 3 CV multiplied by the battery voltage. Battery voltage is 2 volt. So this become plus 6 CV. Okay, plus 6. So this is the okay. Final energy already we have calculated here. Final energy is this one. So denominator we can easily write. Numerator heat generated we have to calculate. So tell me what is heat generated. Heat generated formula is work done by battery. Right, good. So work done by battery minus delta U. So calculate 6 CV minus, this is here 1.5, 1.5 CV. CV or C, oh sorry, 2V is there now. 2V. So CV square it is definitely. Okay, so 6 CV square minus 1.5 CV square. How much this will become? 4.5. No? 4.5 CV square. Right. Now you calculate this. Okay. Now you calculate this. Heat generated has become 4.5 CV square divided by final energy. That one half C into 2V square. So this is nothing but 2 CV square. 2 CV square. 4.5 by 2 is how much? 2.25, right? Yes, this is the answer. Many people will not be able to do this because calculation of heat generated they will get stuck. So this formula we should know, work done by battery minus change of energy. Yes. Okay, so you can work out any type of questions on this. This is over. Now we need to see about the dielectric, insertion of dielectric and the force generated. So suppose there is a capacitor. So this topic is insertion of, effect of inserting dielectric. Effect of effect of inserting dielectric. So case one you take, first case one, battery connected. battery is connected. Battery is connected. So suppose there is a capacitor and a battery is connected like this, plus minus voltage V. So it will have some charge, right? But capacitance is C. But note that battery is connected means the potential across this cannot change. Potential across this will be constant. Battery is connected means potential difference across capacitor. Potential difference across capacitor is equal to constant because battery supplies a constant potential. So potential difference across the capacitor will not change. Okay, right. So now, right now, charge is initially the charge is plus CV minus CV. Now let us insert a dielectric. Suppose now you are making a dielectric. Then what will happen? We are just only inserting dielectric. So dielectric of material, some constant will be there. Okay, some dielectric we have inserted. So now dielectric has K. So capacitance, note that capacitance will become now, capacitance C dash is now K times of C, because capacitance formula is epsilon naught, area by D, epsilon naught changes because medium changes, right? So K times C capacitance, new capacitance. So capacitance will definitely increase. Capacitance increases. Capacitance increases. Capacitance increases. Note that we are not changing the distance between plates. Everything else is same. Only you are inserting a dielectric. So this study which we are doing, you are only inserting a dielectric. So because that capacitance of this system will increase, then what will happen? What about the charge now? Previously this was the charge Q. Now let us say charge is Q dash. Q dash plus Q dash minus Q dash. So now this Q dash will be C dash into V. Remember this V is not changing. Battery is the same voltage. So C dash has become K times, so K times CV. So charge also increases. Charge also increases. So charge increases by, charge also increases. Charge also increases. So charge also increases by the same factor K, just like capacitance increases by the same factor K. Charge also increases. What about other things? Energy. Think about energy. So previously, what was the energy? Energy was half C V square. Half C V square, right? Now, what will be the energy? U dash. It's like energy U dash. So half C dash into V square. So C dash has become K times. So half K times C into V square. That's what. So energy is also increasing by the same factor K times. So everything is increasing by a factor K times. Charge increases, capacitance increases, energy increases, right? Everything is increasing. So we can also say that energy also increases. Also increases. Then what else? What else we can study? Hmm. K will be the material dielectric, they will give a constant it is, right? For a given medium, it is constant. Suppose some medium, they will give 3, 4, some value. Okay. No, 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 no. K is dielectric constant, you know, na, K value is always greater than 1. K is 1 for vacuum. Minimum value is for vacuum. Okay. And K is infinity for metals. You know that. Okay. Then what else? What about the electric field? What about the electric field? Previously, the electric field was how much? See, whenever the idea of electric field come, na, because it's positive and negative, so you know the electric field is sigma by epsilon naught. Remember this formula, okay? Sigma by epsilon naught. So sigma is what? Charge by area. Charge is q by area. So the same formula we can apply now. Electric field, let us say E dash. Electric field is sigma dash by epsilon naught. No, epsilon naught is changing here. Epsilon naught become k times. So sigma dash by k times epsilon naught. Okay, because sigma charge changing, so sigma dash different, and medium changes, so k times epsilon naught. Let's calculate that and check whether it is changing or not changing. So sigma dash is charge q dash by area. Area is same, q dash by area, and this is k times epsilon naught. Q dash is what? What is Q dash? Q dash we have calculated. Q times K times of CV. K times of Q. Q is CV. K times of Q area, and also this is K times. I think K get cancelled, so it is same Q by A epsilon naught. Right? So electric field does not change. Now there is another way to understand this formula. Remember that electric field is potential difference by the distance, okay, V by T. So because the battery is the same voltage and distance between the plate is also same, that is why V is anyway not changing and distance is also not changing. So we can also say like this way also, because V is constant, distance between plate is also same, so it is not changing. Okay, so electric field does not change. Electric field remains same. Remains same. Then what else? Electric field remains same. Energy density, everything is over now. That's all. I think these things they can ask: charge, capacitance, electric field, energy. These things they can ask. So this is the case where battery is connected. Okay, and now we can also study. See, in this case also you can study like while you are inserting, what is the force acting on the dielectric. In this case itself, you study that. So suppose, for example, there was a capacitor connected with a battery, and you were trying to insert a dielectric, and some portion you have inserted. Let us say dielectric you are trying to insert, and some portion X portion you have inserted. X portion you have inserted. So X portion you have already inserted. Remaining was outside. It has not inserted. So remaining this length, let us say length is L, so L minus X is not inserted, X portion is only inserted, so you need to consider this much portion only inserted, this much portion is inserted, right? This much portion, X portion was inserted, remaining L minus X is not inserted, and you can consider that this is the distance between the plates, and plate is like a rectangular plate, so you can assume that the plate has a width also. Plate has a width of b. Okay, or if you want area you can take, it doesn't matter. So plate is like a rectangular plate, right? So what will be the force? See, the idea of calculation of force will depend on, remember, the calculation of force depends on minus du by dx. This is the approach of calculating the force. This is the formula for force on dielectric. Force on dielectric. So you need to calculate the energy stored in this system. Okay. So in this capacitor, if you are taking this, half is filled with some material dielectric, whose dielectric constant you can take K, and this is vacuum. Okay. So half is not half, some portion, X portion is filled, and remaining L minus X portion is not filled. So you can consider it's like a two capacitance system in parallel. The upper one you can take as C1 and lower one vacuum you can take C2. So what will be C1? Let us write C1 K times epsilon naught area by distance. Distance is d only, but what is the area? Let us write area properly. Area will be x into width, x into b, right? Divided by distance is d only. What about C2 capacitance? Epsilon naught area is L minus x into the width d, that is what? By distance d. Okay. So these two capacitors C1 and C2 they are in parallel. So first calculate C equivalent. Calculate C equivalent. Parallel means C1 plus C2. So let us add that C1 C2. D will come common base and epsilon naught B will anyway come out. If you want you can take this. So that is epsilon naught B has come K into X plus L minus X. So little bit arrange it. C equivalent you will get as X terms you can bring common epsilon naught B by D L plus K minus 1 times X. Okay, this is what is C equivalent. So the energy stored in this condition is half C equivalent into V square. This is the energy stored. Let us write the energy stored. So half C equivalent is epsilon naught B by D 1 plus K minus 1 into X, right, into V square. Okay, so we got the energy. Now let us use the force formula. Force is minus du by dx. So force is minus du by dx. Differentiate with x. So things which are common to constant terms take out. Epsilon p d v square comes out. And this 1 plus this term you have to differentiate with x. So 1 differentiation is anyway 0. Here k minus 1 will come. K minus 1. This is what it is, right? And this is and k is greater than 1 and this is a negative term. Negative means attractive force. Attractive force. Okay, so this is the formula for attractive force. B is the width. If it is a square plate, then B can be equal to L. Okay, so if you try to insert a small, there is a capacitor and little bit you put inside, then it will start feeling a force that the dielectric support you insert a little bit inside this. Even x can be small also. So if x portion you insert, and remember battery is still connected here. Battery is connected to the capacitor plate. So this capacitor, this dielectric will start experiencing a force towards it, attractive force. Right. So this will get attracted. Little bit you insert, it will go inside that. Okay. This force is given by this form. Okay. Then next you take the case where the battery is not connected. Battery is disconnected. Capacitor was charged, but battery got disconnected. That case you study. Let us take that case. Are you clear about this? Yes. Okay. Case 2, capacitor charged and battery disconnected. So first let us see the effect of inserting. Inserting means we are assuming completely inserted. You have completely inserted. First of all, you have charged it. So charge, you have used the battery voltage V, so it has got a charge plus CV minus CV. Now you have completely inserted. Here we are studying that what is the effect of completely inserting it. You have completely inserted that. Other things we are not changing, just we are putting this dielectric. Then what happens? So definitely C changes. Remember, C will change to K times of C because medium has changed. Capacitance will change. But remember here battery is disconnected. So whatever charge is there, that charge must be constant. So because battery is not there now to supply an extra charge, whatever charge it has got, that charge has to remain as constant. So no charge will not change here. Even if you put a dielectric, charge does not change. Q does not change. Q does not change. Q will not change. So we can think of the simple formula because Q is equal to C into V, and because charge cannot change, the product must remain constant. Product must remain constant. So if C increases K times, then voltage has to decrease because V will be inversely proportional to C. Now the potential difference across the plate will change. So because previously the voltage was V, now the voltage will be V by K. Why? Because see, you are increasing it. So voltage will decrease by the same factor. So when you put a dielectric and battery is not there, it was already charged, then the voltage across the plate will decrease. Okay. Then what about the field and energy? Let us calculate first energy. Energy was half CV square. Previously energy was there. So energy formula we have to use in terms of charge. Remember why? Because charge is constant. So in terms of charge you use. So energy formula we will use Q square by 2C. Q square by 2C. So here also same effect will happen because Q is constant. So U is inversely proportional to capacitance. So capacitance is increased, energy will decrease. So energy will change U by K. If energy was U initially, now energy will be K times smaller. What about the electric field? Electric field also you check now. If you apply the same logic, electric field is V by D. Distance we are not changing. So V is changing, right? V is decreasing, so electric field will decrease. Here also same factor. So electric field change from E to E by K. Clear? So these are the things that will change. So what are the things changing? C will definitely change, charge will not change, voltage will change, decrease, energy will also decrease, then electric field will also decrease. All these things will happen. Okay, now here what about the, if you are partially trying to insert, what will be the force? Same approach you try. Force when inserting dielectric. So here battery is not connected, it has already got charge, but you are trying to insert a dielectric. Some distance x you have already inserted. So x distance we have inserted, L minus x distance not inserted. Okay, so here the dielectric constant is K, same way. So again here also C equivalent you calculate first. I think we have already calculated C equivalent previously. C equivalent we have already calculated, right? This we have taken as width B and this length we have taken as L. So what was the C equivalent? Epsilon naught B was common, I think, right? Epsilon P by D, L plus K minus 1 times X. This was the correct? C equivalent we calculate. Okay. So energy formula, how to write energy formula now? Because remember charge is constant. So write in terms of charge. Okay. So energy will be Q square by 2C equivalent. Q was already some constant C into V. Previously it was there. It is constant. Okay. So force is equal to minus du by dx. How do we now calculate this force? Now here note that charge is constant. So while you are differentiating this, q square by 2 terms will come out, and you have to differentiate 1 by c equivalent with respect to x. Chain rule you have to apply here. So minus q square by 2 differentiation of 1 by c equivalent with respect to c equivalent, and differentiation of c equivalent with respect to x. Chain rule. Let us apply this chain rule. So minus q square by 2, c equivalent differentiation becomes minus 1 by c equivalent square. Then differentiation of c equivalent, we have already calculated that epsilon naught b by d, L differentiation 0, this is k minus 1. Okay, so how much are we getting here? Minus minus become plus. K square by 2 c equivalent square. Whatever that is, c equivalent square, c equivalent, if you want, write it. Square, that is also a square. Okay, so let us not simplify it. I will keep it like this. C equivalent square, epsilon b k minus 1 by t. Okay. What about C equivalent square? C equivalent square will come as a function. If you want, you write it one step just to show that how complex this formula looks like. So q square by 2 C equivalent is epsilon naught b by d L plus k minus 1 times x. Right? This whole square is equivalent epsilon naught b by k minus 1 into t. So also this is in the denominator. So here note that definitely this force is not constant, right? Because this force is depending on x. As you change the x, force will change. So this force is not constant. It is not constant. But in that case, it was a constant force. Here force is not constant. And here it looks like this is a positive. So there can be a repulsive force also here. There will be a repulsive force, and force is a variable. Suppose x is 0. Suppose x is 0 means you have not inserted, then this is the simple formula. But as soon as you are inserting, so x is increasing, right? And x increases, then what happens? This term will increase, and denominator increase, that means it will decrease. So as you are inserting more and more, force decreases. Initially force was large, and after that force is small. So force is decreasing, and it's a repulsive force. Okay, so repulsion is there, but the repulsion force decreases as you insert more and more. So this is what it is. So this is all about the insertion of the dielectric. So I think this topic is over. Capacitor is complete now. Right? So you need to start now, complete this one. Next we are going to start current electricity, which will be the next new chapter. It's a high weightage topic, but many things will be similar, like the Kirchhoff's law and some circuit ideas. Those will be similar. Only thing is that instead of capacitor, it will be a resistor. Okay, fine. So let's wind up here. Now you work out the worksheet is already sent, right? You please work out the questions. At least worksheet 1 you do. Okay, then you'll get some good idea about that. Okay, fine. Okay, then we'll see you next class. Bye bye. Yes.